Imagine this. You're standing in a pitch-black desert, holding the brightest flashlight in the world. Its beam cuts through the darkness, revealing sand dunes, rocks, and strange shadows. But no matter how powerful the light is, there's always a limit. There's always a distance where the darkness wins. Now replace the desert with the entire universe. Replace your flashlight with the speed of light. And now ask, what lies beyond the final reach of our light? Hello and welcome. I'm John, coming to you from Infinite Universe NTH. Today, we're going on a journey that pushes against the very edge of reality. We'll explore what lies beyond the observable universe, a place where science, imagination, and mystery collide. But before we head into the unknown, let's first understand where our known ends. The term observable universe might sound like science fiction, but it's actually very simple. It refers to everything we can see or detect from Earth right now, based on how far light has had time to travel since the universe began. Light doesn't move infinitely fast. It travels at 299,792 kilometers per second, or about 7.5 times around Earth in 1 second. That's fast, but not instant. The universe began about 13.8 billion years ago, so you might think the observable universe is 13.8 billion light-years wide. But that's not quite right. Here's where things get tricky and fascinating. Because while light was moving through space, space itself was expanding. Think of a loaf of raisin bread baking in the oven. As the dough rises, all the raisins move away from each other, not because they're moving, but because the bread between them is growing. Now imagine light as one of those raisins trying to reach you, but the bread is stretching faster than it can travel. So how big is it really? The farthest light we can detect has traveled for 13.8 billion years. But because of cosmic expansion, the source of that light is now much farther away than that. In fact, the radius of the observable universe is about 46.5 billion light-years. That means the full observable universe is a sphere 93 billion light-years wide. Let that sink in. We're looking at a sphere so large that a beam of light would take 93 billion years to go from one side to the other. And that's just the part we can see. The key word is observable. Here's a way to picture it. You're sitting in the middle of a giant black ocean. You shine a light. The light reaches a certain distance, but no farther. That bubble of visibility, that's your observable universe. But you know the ocean continues. You may not be able to see it, but it's still out there. That's how astronomers view the universe. They call it our Hubble volume, the region of space from which light has had enough time to reach us since the Big Bang. And the amazing thing is, everyone has their own observable universe. If you were standing on a galaxy 10 billion light-years away, your view of the cosmos would look completely different. Different stars, different galaxies, different boundaries, but the physics would remain the same. Now here's a weird thought. In every direction, the observable universe stretches equally from Earth. So, are we in the center of the universe? Not at all. We're at the center of our visible universe, simply because light reaches us from all sides equally. It's the same for any other point in space. In fact, from the perspective of an alien in another galaxy, they'd be the center of their own observable universe. The observable universe isn't like a stage we're standing in the middle of. It's more like a personal light bubble, shaped by time and speed. Here's the real kicker. When we look farther into space, we're also looking back in time. The moon? 1.3 seconds ago. The Sun, 8 minutes ago. The nearest galaxy, Andromeda, 2.5 million years ago. The edge of the observable universe, 13.8 billion years ago. We're not just seeing objects far away. We're seeing their ancient past, a snapshot frozen in time. It's like reading messages in bottles that have been floating across the cosmic sea for billions of years. And beyond that, there are bottles still in transit, light still traveling toward us. We just haven't seen them yet. Or maybe we never will. All right. So we've established that we live inside a bubble of light, a 93 billion light-year wide sphere called the observable universe. But here's the next big question. Why can't we see what's beyond that bubble? Is there a wall, a force field, a cosmic curtain hiding the rest of the universe? Not quite. The answer, like most things in cosmology, comes down to three simple limits: time, light, and space itself. Let's unpack each one. Our universe is around 13.8 billion years old. That means the farthest anything can travel to reach us, whether it's light, particles, or even gravity, is 13.8 billion light years. Just like if you started a stopwatch 10 seconds ago, the farthest anything could have moved at 1 meter per second is 10 meters. We call this boundary the cosmic light horizon. Anything beyond that horizon, its light simply hasn't had time to reach us yet. It's not invisible because it's hidden. It's invisible because we're too young to see it. Give it another 10 billion years and we'll see farther, assuming the universe cooperates. But does it? Let's take a moment to appreciate light. It's the fastest thing in the universe, but it's still not instantaneous. It takes 1.3 seconds for light from the moon to reach us, 8 minutes from the sun, 4.3 years from Proxima Centauri, over 2 million years from Andromeda, and 13.8 billion years from the oldest light we can detect. So imagine, there could be a galaxy 100 billion light years away. It might be there, it might be glowing, but its light won't reach us for tens of billions of years, if ever. Until that light arrives, it might as well not exist, from our perspective. In other words, our vision of the universe is a time capsule, a collection of light messages, each with its own timestamp. Here's where it gets truly mind-bending. Light is trying to travel to us from distant galaxies, but the fabric of space, the very stage light is moving through, is expanding, not slowly. In some places, it's expanding faster than light. And before you ask, yes, that's allowed. Einstein's laws say that nothing can move through space faster than light, but space itself can stretch at any speed. Think of light as a swimmer and space as a river. If the river flows faster than the swimmer can swim upstream, the swimmer never reaches you. That's exactly what happens to light from extremely distant galaxies. It gets caught in the current. The space between us and that galaxy is stretching faster than light can cross it. So that light, it never arrives. It's redshifted into oblivion, its wavelength stretched so long it becomes undetectable. Here's something even more chilling. As space expands, some galaxies that we can see today will eventually disappear. Their light won't be able to keep up with the expanding space, and in a few trillion years, they'll fade from view completely. Future civilizations might see a night sky nearly empty, only their own galaxy, and perhaps a few neighbors. To them, the universe will look like a lonely place. But it's not that the universe shrank. It's that their observable universe got smaller, because expansion erased the light from everything else. We live in a very special time, a moment when the universe is still big enough and bright enough to be explored. We are cosmic toddlers, just barely old enough to open our eyes. Here's a simple way to understand all this. Imagine you're in a huge stadium at night. You're holding a candle. The flame lights up a small circle around you. That's your observable universe. But as time passes, your candle burns brighter. Your vision expands. You begin to see more of the stadium. But now, imagine that the stadium itself is inflating, growing larger every second. You see more, sure, but the walls are racing away from your light, and some parts move so fast, your candle will never reach them. No matter how long you wait, no matter how bright the flame becomes. That's where we are now, living in a dark, expanding stadium, seeing only what our fragile little flame of light can reveal. Even weirder? Some of the galaxies we do see now don't exist anymore. They may have merged, collapsed, or transformed billions of years ago. The light we're seeing is ancient history, like watching a documentary filmed eons ago. In a way, telescopes are time machines, but imperfect ones. We can look into the past, but we'll never know what's happening now in those distant corners of the universe. And even if we could travel at the speed of light, we still wouldn't catch up to those fleeing galaxies. They're gone, out of range, out of time. So, why can't we see beyond the observable universe? Because of the age of the universe, light hasn't had time to reach us. The speed of light, even the fastest thing, has its limits. The expansion of space. Some things are literally moving away faster than light. Put simply, the observable universe isn't a hard wall. It's a boundary drawn by light, time, and motion. It's not what's out there that limits us. It's the way the universe works. So far, we've learned where the edge of our vision is and why we can't see beyond it. But now, let's go farther. Let's imagine that somehow we could step outside our light bubble or peek past the curtain of cosmic time. What would we find? No one knows for sure, but cosmologists have three leading ideas, each one more fascinating than the last. Let's dive in. This is the simplest explanation, and ironically also the most mind-blowing. It says that beyond the observable universe lies just more universe, more galaxies, more stars, more space, endlessly, no edge, no special border, just an infinite cosmic stretch of the same stuff we already see. Imagine being on a ship in the middle of the ocean. You see waves in every direction. No land, no wall, just more ocean. That's the idea here. Our observable universe is like one drop in an infinite sea. And here's the crazy part. If the universe is truly infinite and matter is distributed evenly enough, then, statistically, there are infinite combinations of matter. That means every possible configuration of atoms eventually happens, including you. Somewhere out there, there may be another version of you, eating a slightly different breakfast, living in a galaxy shaped like a cube, or maybe a version that never existed at all. It sounds like science fiction, but mathematically, it's not impossible. This is sometimes called the infinite Earth hypothesis, and it's one of the wildest implications of an infinite uniform universe. What if the universe isn't uniform? What if beyond our observable bubble, the laws of physics themselves change? This brings us to a theory called eternal inflation. Here's how it works. Right after the Big Bang, space didn't just expand, it inflated, super fast, faster than light. And according to the math, that inflation never stopped entirely. It just slowed down in some regions, like ours. In other regions, it kept going. Those regions formed other bubbles, other pocket universes, each one with its own Big Bang, and maybe its own rules. Imagine a pot of boiling soup. Each bubble on the surface is a separate universe. Some are big, some are small, some explode, some fade, but all are disconnected, isolated, and evolving on their own. Our universe would be just one bubble in that boiling cosmic foam. Some bubbles might have no stars, others no atoms. Some might operate on entirely different laws, where gravity is repulsive or light doesn't exist. This is where science begins to blur with imagination. But the idea comes from serious physics. Inflationary models supported by cosmic microwave background data. And if it's true, then we're not just in a universe, we're in a multiverse. The third idea is less flashy, but deeply elegant. It suggests that the universe might not be infinite at all. Instead, it might be finite, but without edges. Think of the surface of Earth. You can walk in a straight line forever and never fall off. Eventually, you loop back to where you started. This is called a closed, curved universe. Not flat like paper, not open like a saddle, but curved like a sphere, or more precisely, like a higher dimensional object called a three-sphere. In this model, the universe doesn't go on forever, but it also doesn't have a wall, a boundary, or an outside. It wraps back around on itself. So, if you had a super telescope and could look far enough in one direction, you might eventually see the back of your own head, millions of years in the past. Okay, that's hypothetical, but you get the idea. This kind of universe could still look infinite to us. Because the curvature is so gentle, we don't notice it. It's like standing in the middle of a football field and saying, "Yep, the Earth is definitely flat." We just can't see far enough to spot the curve. So while it feels infinite, it might just be looping. So, which theory is correct? The truth is, we don't know yet. We don't have direct evidence for any of them. But here's what we do have. Observations suggest the universe is very flat on large scales. Inflation theory fits very well with cosmic background radiation. The expansion of space implies some regions are permanently unreachable, and math shows that an infinite repeating universe is possible. The deeper we look, the more each idea seems to fit in pieces, like fragments of a puzzle that hasn't been solved. And maybe that's the point. Each theory, whether it's infinite sameness, cosmic patchwork, or finite curvature, forces us to confront our own limits, not just in technology, but in imagination. How do you picture something with no edge, or a place where physics stops making sense, or a version of yourself in another universe? That's the magic of cosmology. It's not just about stars and galaxies. It's about pushing the boundary of what we can even think about. All right, let's recap. So far, we've explored what the observable universe is, why we can't see beyond it, and the leading theories about what might lie on the other side. But now comes the real challenge. How do you study something you can't see and never will? That's what scientists have been trying to do for decades, not with sight, but with mathematics, radiation, and clues left behind in the fabric of space itself. Let's take a look at how we peer into the dark. First up, the CMB, or cosmic microwave background. This is the oldest light in the universe, a glow from when the universe was just 380,000 years old. Before that, everything was too hot, too dense. Atoms couldn't form, light couldn't escape. It was like living inside a fog. But when things cooled down just enough, light broke free. And it's been traveling ever since. In 1965, we detected it by accident. Today, we've mapped it in astonishing detail. It's a nearly uniform glow coming from every direction, but with tiny fluctuations, like temperature fingerprints from the Infinite Universe. And here's the incredible part. Those patterns in the CMB give us clues about the shape of the universe, its age and density, whether space is flat, open, or curved, and whether something beyond what we see is pulling on our observable universe. Think of it like a ripple in a pond. Even if you can't see the stone that made the ripple, you can feel its effect. The CMB is a message from the beginning, and it's still speaking. Now this one's weird. In 2008, scientists noticed something strange. Clusters of galaxies were moving in the same direction at very high speeds, faster than they should, and in a way gravity alone couldn't explain. This mysterious movement was dubbed dark flow. It's as if something massive, something outside the observable universe, was tugging on them. We can't see what it is. We don't even know if it's real. Some think it's an error in the data. Others believe it may be evidence of structures beyond our cosmic horizon. Imagine pulling on a bedsheet from outside the camera frame. You don't see the hand, just the stretch. That's the idea behind dark flow. If it's real, it could be a sign that our observable universe is just part of a much larger structure, one that's interacting with us across the edge of visibility. A cosmic tug-of-war, with one side hidden. It's one of many clues that remind us. The invisible doesn't mean the irrelevant. Let's zoom out, way out. If you map the position of galaxies across the sky, you'll notice something amazing. They're not scattered randomly. They form a kind of cosmic web. Galaxies group into clusters. Clusters form filaments. Filaments frame vast empty regions called voids. This massive structure, called the large-scale structure of the universe, gives us hints about how gravity shaped matter over billions of years. And by studying how these patterns form and evolve, scientists can simulate how space might behave beyond the observable edge. It's like watching waves in a pond and guessing what's just out of view. If a wave is coming in from outside the camera frame, you can predict where the disturbance began, even if you never see the rock that made it. That's how we treat the universe. By looking at what's moving, we try to understand what pushed it, even if that push came from a place we can't see. It's indirect, but it works. It's cosmic inference, and it's one of the best tools we have. Another powerful tool isn't telescopic. It's mathematical. Cosmologists measure the curvature of space by looking at how light bends, how galaxies cluster, how the CMB varies across the sky, and so far, the results suggest the universe is flat, very flat. Like so flat that if space were a giant pizza, the thickness of the crust compared to the diameter would be less than the width of a proton. And what does a flat universe imply? Usually one of two things. It's infinite, or so big and gently curved that we can't detect the curve yet. Either way, this flatness gives weight to the idea that there's far more beyond our current horizon. It's like standing in a vast, foggy plain. You see no curve. But that doesn't mean the Earth is flat. It just means your eyes aren't good enough. Yet. Right now, the James Webb Space Telescope, JWST, is peering deeper into space and further back in time than any tool before it. It can detect infrared light from some of the first galaxies ever formed. But even JWST can't break the barrier of the observable universe. Still, it can help us. Refine our models of early expansion, understand how galaxies form across time, test predictions from inflation and dark matter theories. Meanwhile, future missions like LISA might detect gravitational waves from events far beyond what light can show us. And who knows? Maybe one day we'll find a new kind of light, a way to detect information from across the boundary. The frontier is always moving. Even though we're limited to what we can observe, we're not powerless. We've learned to read the ancient glow of the early universe, detect subtle motions across billions of light years, model the shape and scale of all existence, and build machines that reach deeper into the dark than ever before. In a way, we've become cosmic detectives, solving a mystery with clues left behind by the biggest explosion in history, the Big Bang. So, we've come to the end. We've traveled from the center of our visible cosmos to the unreachable edge of light and time, and we've imagined what might lie beyond. But there's one final question left to ask. Why does it matter? Why should we care about what lies beyond the observable universe, if we may never see it, never go there, and never know it with certainty? Let me show you why. Every atom in your body was once forged in the core of a star. That star was born from the dust of galaxies, which came from clouds of hydrogen, which formed after the Big Bang. You are not just in the universe, you are of the universe. And the fact that the universe can evolve to stars, to life, to consciousness capable of asking these questions, that's astonishing. Studying the cosmos is not just about galaxies or theories. It's about understanding who we are and where we fit in the grandest story ever told. If we could see beyond the observable universe, we might find countless galaxies, an infinite sea of matter, or perhaps nothing at all. But maybe what's more important is that we've already come this far. From ancient stargazers mapping the sky by firelight, to space telescopes capturing the afterglow of creation, from myths of gods and chariots, to inflation theory and multiverse models. Each generation has looked up and asked, what lies beyond? And even without clear answers, that question has driven progress, technology, and wonder. It's pulled us forward, light year by light year. Throughout this journey, we've talked about edges. The edge of light, the edge of time, the edge of what physics allows. But perhaps the most important edge is the edge of our own understanding. As technology advances, that edge will move. But there may always be parts of the universe we'll never reach. Not because they're far away, but because they lie beyond what the human mind can truly comprehend. And that's okay. Because mystery is not the enemy of knowledge. It's the fuel. Let's go one step further. If we ask what lies beyond the observable universe, we also have to ask, what happens to it all in the end? Here are three possibilities scientists propose. The universe continues expanding. Galaxies drift apart. Stars burn out. Matter decays. Eventually, all that remains is cold, dark emptiness. No new stars, no new light, just black holes evaporating into nothing. A slow, silent end. No bang, no scream, just stillness. Dark energy grows stronger. Eventually, it pulls galaxies apart, then star systems, then planets, atoms, even space-time itself. A catastrophic unmaking of everything. Not just an end, but a tearing apart of reality itself. The universe doesn't fade, it snaps. Maybe the universe contracts one day, collapsing back into a singularity. And from that collapse, a new Big Bang is born. A new universe, a new story, an eternal cycle. It's rebirth instead of death, restart instead of silence. We don't know which one is true, but each tells us something profound. Nothing lasts forever, not even the universe. And yet, here we are, living at a time when the stars still shine, when the light from the beginning still reaches us, when we can ask questions, build telescopes, and imagine beyond imagination. That, in itself, is extraordinary. We exist at a rare moment, when the cosmos is old enough to reveal its secrets, but young enough for us to still witness them. A cosmic window, and we're here for it. Sometimes people say, thinking about the universe makes me feel small. But I don't think that's true. Because to feel small, you must already understand the scale of something greater. To even ask, what lies beyond, means you are already bigger than that boundary. Not in size, but in spirit. You are a piece of the universe, with the rare ability to reflect on itself. Tonight, when you look up, remember that every point of light you see is just the beginning. Beyond that glow, beyond what we can measure, beyond the farthest galaxy, there may be more. And though we may never reach it, the very act of wondering connects us to something eternal. This is John, signing off from Infinite Universe NTH. See you in the next frontier.